The geology of the Moon is quite different from that of Earth. The Moon lacks a true atmosphere, which eliminates erosion due to weather. It does not have any known form of plate tectonics. It has a lower gravity, and because of its small size, it cooled faster. The complex geomorphology of the lunar surface has been formed by a combination of processes, especially impact cratering and volcanism. The Moon is a differentiated body, with a crust, mantle, and core. Geological studies of the Moon are based on a combination of Earth-based telescope observations, measurements from orbiting spacecraft, lunar samples, and geophysical data. 6 locations were sampled directly during the crewed Apollo program landings from 1969 to 1972, which returned 380.96 kilograms in 2020. The Moon is the only extraterrestrial body for which we have samples with a known geologic context. A handful of lunar meteorites have been recognized on Earth, though their source craters on the Moon are unknown. A substantial portion of the lunar surface has not been explored, and a number of geological questions remain unanswered. Elements known to be present on the lunar surface include, among others, oxygen, magnesium, manganese, carbon and nitrogen appear to be present only in trace quantities from deposition by solar wind. For a long period of time, the fundamental question regarding the history of the Moon was of its origin. Early hypotheses included fission from Earth, capture, and co-accretion. Today, the giant impact hypothesis is widely accepted by the scientific community. The geological history of the Moon has been defined into 6 major epochs, called the lunar geologic timescale. Starting about 4.5 billion years ago, the newly formed Moon was in a molten state and was orbiting much closer to Earth, resulting in tidal forces. These tidal forces deformed the molten body into an ellipsoid, with the major axis pointed towards Earth. The first important event in the geologic evolution of the Moon was the crystallization of the near global magma ocean. It is not known with certainty what its depth was, but several studies imply a depth of about 500 kilometers or greater. The first minerals to form in this ocean were the iron and magnesium silicates, olivine and pyroxene. Because these minerals were denser than the molten material around them, they sank. After crystallization was about 75% complete, less dense anorthositic plagioclase feldspar crystallized and floated, forming an anorthositic crust about 50 kilometers in thickness. The majority of the magma ocean crystallized quickly, though the final remaining crip-rich magmas, which are highly enriched in incompatible and heat-producing elements, could have remained partially molten for several 100 million years. It appears that the final crip-rich magmas of the magma ocean eventually became concentrated within the region of Oceanus Procellarum in the Umbrium Basin, a unique geologic province that is now known as the Procellarum crypteran. Quickly after the lunar crust formed, or even as it was forming, different types of magmas that would give rise to the Mg-sweet norites and troctolites began to form. Although the exact depths at which this occurred are not known precisely, recent theories suggest that Mg-sweet plutinism was largely confined to the region of the Procellarum crypteran, and that these magmas are genetically related to crypt in some manner, though their origin is still highly debated in the scientific community. The oldest of the Mg-sweet rocks have crystallization ages of about 3.85 Ga. However, the last large impact that could have excavated deep into the crust also occurred at 3.85 Ga before present. Thus, it seems probable that Mg-sweet plutonic activity continued for a much longer time, and that younger plutonic rocks exist deep below the surface. Analysis of the lunar samples seems to imply that a significant percentage of the lunar impact basins formed within a very short period of time between about 4 and 3.85 Ga ago. This hypothesis is referred to as the Lunar Cataclysm or late heavy bombardment. However, it is now recognized that ejecta from the Umbrium impact basin should be found at all of the Apollo landing sites. It is thus possible that ages for some impact basins could have been mistakenly assigned the same age as Umbrium. The lunar maria represent ancient flood basaltic eruptions, In comparison to terrestrial lavas, these contain higher iron abundances, have low viscosities, and some contain highly elevated abundances of the titanium-rich mineral ilmenite. The majority of basaltic eruptions occurred between about 3 and 3.5 Ga ago, though some mare samples have ages as old as 4.2 Ga, and the youngest are thought to have erupted 1 billion years ago. Along with mare volcanism came pyroclastic eruptions, which launched molten basaltic materials hundreds of kilometers away from the volcano. A large portion of the mare formed, or flowed into, the low lava,